when you try to look at compounds like aluminum fluoride, where aluminum has to form Al plus 3. Now, obviously, forming plus 3 is a huge deal because you have to go from +1 to +2 to +3. So you need 3 ionization energies and each one is increasing. So it's a huge, big number. And fluorine, when it forms fluoride, it's not releasing so much energy. We know that fluorine releases less energy than chlorine also, right? But in spite of that, the aluminum requiring so much energy and fluorine not releasing so much, still aluminum fluoride is an ionic compound. How come? How come aluminum fluoride is an ionic compound even though aluminum has to form +3 ion, which means 3 electrons have to be lost, which is a huge value of energy? That is because of lattice energy. Now, what is lattice energy? Now, when you look at the Born-Haber cycle, which we've done earlier, if you remember the Born-Haber cycle, sodium has to first give, sodium solid has to first give you sodium gas, which is a requirement of energy, sublimation energy. And then sodium gas has to form sodium plus gas, which is also a requirement of energy, which is ionization energy. Chlorine, you want to break and form chlorine atoms, which is a requirement of energy, bond dissociation energy. And then after chlorine gas, you have to form chloride ions. This is the only one which is a release of energy. 3 requirements of energies, only 1 release of energy. It can't compensate. But then you end up having another extra type of energy which compensates for all these required energies. And that energy is nothing but when you take the 2 gas ions and form the solid state of your ionic compound. When you put these ions together and form a solid from them, it releases an energy, and that release of energy is called lattice energy, which is so huge that it compensates all the required energies, even if it requires 3 energies. Which I mean, like in case of aluminium, after aluminium solid gives aluminium gas, it has to form the cation 1, it has to form the cation 2, it has to form the cation 3. After that, fluorine will give you fluorine atom, which will later on give you fluoride ion. All this required energy, from here to here, everything is required, is compensated by aluminium plus 3 and 3 fluorides coming together to give you aluminium fluoride solid. This is lattice energy, which is able to compensate every other required energy. So that is why aluminium fluoride exists as an ionic compound. The same thing if I talk for, let's say, boron fluoride, BF3. Boron requires a huge amount of energy to go into B+3 gas. From here to here, it's a huge amount of energy. Obviously, fluorine giving fluoride is small, but later on, after these two combine and give you BF3 solid, still the energy is not able to be compensated. AlF3 low, the energy is able to be compensated. In BF3, the energy is not able to be compensated. So that's why BF3 will not form ionic compound. Whereas your AlF3 is able to form ionic compound because the energy is able to be compensated. So lattice energy, there are 2 ways of defining it. It is the amount of energy released when the solid structure of the ionic compound is formed, or it is the amount of energy required to break up the solid structure of your ionic compound. The amount of energy released when the solid structure is formed, or the amount of energy required to break up the solid structure. Both of them are the definition of lattice energy. Na plus ion and Cl minus ion, galig tirutunnayi atu itu. So their interactions are going to change. Kasep daggaraga untadi, so ekkuva. Kasep duranga untadi, so takkuva. Opposite ions always like staying together. So if I can bring the sodium ion, make it sit in one place, I'm going to represent that with a plus sign, and surround it with anions. And then each anion also again surround with cations. And then the cation again with anions. So this kind of alternate surrounding each other kind of an arrangement, if you go on doing it in all directions, this gives you the crystal structure of sodium chloride. That is converting the gas form into a solid state. Get them all together, put them with each other, and you're going to get an ionic crystal. Now, about ionic crystals and the structures, detailed we will study in solid state chapter. But here we are going to do just the basic points that we need, which is when you are getting these sodiums and chlorines, which are garlic tiruthunai kada, aa garlic tiruthuna sodiums ni chlorines ni, when you get them and make them sit in these positions and give them the required interaction on all sides, chakkaga sodium ni surround chestunnaru on all sides with chlorine. Daniki ishtam adi, because opposites attract. Ala chesinappudu a lot of energy is released, and this released energy is called lattice energy. Now, when you try to break the crystal also, this is the same energy required to break a crystal. Why would I want to break a crystal? If you want to move sodium and chlorine away from each other, the amount of energy required to break the crystal, that is also called lattice energy. So, lattice energy ki rendu perlu untai. It is the amount of energy required to break the crystal or the amount of energy released when the crystal is made. Ela chuskunna okate. So when you make the crystal, the energy is released. When you break the crystal, energy is required. This is called lattice energy. And this is a huge value. It is so huge that it compensates all the required energies. And in fact, if you look at the Born-Haber cycle, required, this is the only released energy. But this lattice energy is so huge that overall it makes the heat of formation negative for all ionic compounds, not just this ionic compound. The definition of lattice energy: the energy released when 1 mole of a crystal is formed with sufficient number of cations and anions coming together in their gaseous state is called lattice energy. So when you have Na plus gas and Cl minus gas coming together and forming NaCl solid, when 1 mole of such a solid is formed, that is called lattice energy. Suppose you want to form magnesium chloride, you should take magnesium plus 2 gas, 2 Cl minus gases, such that they form MgCl2 solid. That is called the lattice energy. You should take sufficient number of ions. This amount of energy required to break up the crystal or the amount of energy released when a crystal is made, both are same. If you're breaking up the crystal, then it is required energy. If you're making up the crystal, then it is released energy. Magnitude is the same. So the definition of lattice energy, you can define it either as required energy or released energy. Magnitude wise, it's the same. You cannot measure lattice energy also directly. So in order to measure lattice energy, what we do is use the Born-Haber cycle. So it deals with crystal formation. That is what you have to look at. So when crystals are formed, and crystals are formed in case of ionic compounds, not in case of covalent compounds. In covalent compounds, the kind of crystal that is formed does not involve ions. We will look at covalent crystals in the future in the chapter called solid state. Till then, for us, covalent compounds don't form crystals. Ionic compounds are the ones which form crystals. Now, once your cation and anion are formed, the energy that is released when you try to form the solid structure, that is called your lattice energy. Overall, all these values, if you practically check, they add up to give you your heat of formation.